Alright guys, so this is technically 7.3, but we're going to continue on page 49 and 40, or 39 and 40 rather. We're going to talk about similar triangles, which is kind of the same thing as similar polygons. We don't need any words worth knowing, so you can skip that. These were some of the notes that we took last time, and we're going to go right to page 40, and we're just going to finish filling this out. We might do a couple examples, so hopefully you guys didn't glue this down. I'm going to do a couple examples under there maybe. This really shouldn't be too hard because we hopefully remember how to prove triangles congruent, and to prove triangles similar is basically the same thing. You actually need less stuff though, so that's kind of nice. So, proving triangles similar, we have 3 theorems that we're going to talk about. We're going to talk briefly about indirect measure. That's actually the most important thing here. That's probably what we'll do in class, so that's fun. Alright, so first one, proving triangles similar. If 2 angles of one triangle are congruent to 2 angles of another triangle, this is a comma, then the triangles are similar. And remember the symbol for similar is a little tilde, okay? Basically what this is saying is if you can look at a picture and find that 2 angles, so this is the angle-angle similarity, if you can find that 2 angles are congruent, then that's enough information to say that the triangles are similar, which that's not very much at all. So what you'd be looking at is in some sort of picture you have triangle ABC, and then triangle DEF. And if they told you that A was congruent to E and B was congruent to D, then you'd have enough information, because you have 2 angles on one triangle congruent to 2 angles on the other, to say that the triangles are similar. So you could say that triangle A, B, C is similar to triangle, and you have to make sure that you match them up. So A goes with E and B goes with D. Like that. So hopefully pretty easy. So like you're going to be looking at a picture, and either they will mark angles for you, or you can look for things that will give you that angles are congruent, like vertical angles or maybe some parallel lines and things like that. Okay, and the next one that we have, if the sides of 2 triangles are proportional then the triangles are similar. And that means all the sides. So I'm going to put a little 3 next to that. And this is basically saying if all 3 sides are proportional to all 3 sides, so this is side, side, side similarity, then the triangles are similar. So an example of that might look like I have triangle ABC over here, and then maybe triangle DEF over here. If I know that this side is 3, 4, and 5, and then this side over here is maybe, I don't know, 6, 8, and 10, well, that's really easy to see, hopefully, but, you know, we should check. We want to check that the sides of the 2 triangles are proportional to one another. So I match up the smallest side with the smallest side here, so 3 over 6. And I'm asking myself the question, is that the same ratio as the middle side, like the middle length, so 4 to 8? And then is that also the same as, because all 3 sides have to be proportional, the longest side, which is 5 to 10. And since these are all half, then they are proportional, and so these triangles are similar. So you could say that triangle ABC is similar to triangle, and you want to make sure again that you line them up, so DEF. Now that one was pretty easy. They might not all be that easy, but and truthfully you didn't have to do the small triangle on top and the big triangle on bottom. You could switch it around, then all the ratios would just be 2 over 1, and that's okay, as long as all the ratios are the same and you're consistent. Okay, then the last theorem that we have, if the sides of one triangle no, that can't be right. Hold on, I gotta figure out what the heck I wrote here. If if the two sides, I think I just put of one twice, oops. So if two sides of one triangle are proportional to the lengths of two corresponding sides of another triangle, and then the included angles are congruent, then the triangles are similar. So sorry that was a bit confusing. I just added in that extra line there that I didn't need. So if the two sides of one triangle are proportional to the two lengths of two corresponding sides of another triangle, and the included angles are congruent, remember included means like in between, then the triangles are similar. So really what this is saying is that you have two sides with an angle in between. So this is side angle, side similarity. All the other ones don't actually work. So these are the only three theorems you can use to prove that triangles are similar. And so what that would look like is maybe I have triangle ABC right here, and triangle DEF over here. Maybe I know that this is 10 and 2, and this is 5 and 1, and I know that angle A is congruent to angle D. Well, so I can clearly see that angle A is congruent to angle D, but I also have to check that the two sides are proportional. So if I start with this triangle, I'd start with 10 over the corresponding side on the smaller triangle, which is 5, because those are both the longest sides. Is that the same as 2 to 1? Well, hopefully you know that it is, because 10 over 5 reduces to 2 over 1. And so they are in proportion. And so since these two sides are proportional to these two sides and the angle in between is congruent, these triangles are similar. So really you're just checking to see if one of those three theorems will prove your triangle is similar or not. Why that's useful is for this indirect measure thing. We can set up similar triangles to find the measure of lengths that are too difficult to measure directly. So indirect measure allows us to find lengths that are difficult to measure directly. Meaning, like, if I walked over to it, I couldn't just take out a ruler and measure it. Maybe it's too tall or too far away or something like that. So a really good example of that might be if I wanted to measure how tall the towers are on the Mackinac Bridge or something like that. I can't do that. They're too tall. So I can set up similar triangles to figure out that height. Let's do one like that. Why not? Underneath here, let's say I'm standing right here. It's me. And let's say we know that I am 6 feet tall, which is a little untrue, but we'll go with it. Let's say over here, I have a flagpole. With a flag on it. Look at that, lovely. What I do know is I know the height of how tall I am. I also know how I can measure like how far away I am from the flagpole. So let's say, for instance, I know that I'm a total of, well, you know what? Better yet, let's say, okay, right here, we put a mirror. Because that's really what we need if we want to do some indirect measure. And so I walk back until I can see the top of the flagpole in there. And so I know how far I had to walk away from that mirror. And let's say that it is, 7 feet. I can also measure how far the mirror to the flagpole is. So let's say that that's, 42 feet. I don't really need to know these heights because these angles right here that the reflection is bouncing off of, will always be the same. These angles right here are both 90 because I'm perpendicular with the ground, and so is the flagpole. And so really what I have here is side angle, side similarity, or what I should have. And so because these angles are congruent, I can set up proportions. The distance from the mirror, these two things are in ratio with one another, and then my height to the flagpole's height, which I don't know, I can set up that ratio as well, and they should be equal. So if I start with me and my little triangle right here, I could say that my height over the distance away from the mirror is equal to the height of the flagpole, which I don't know, over the distance from the mirror, so 42. And so then we could cross multiply and solve. And so 7 times x is just 7x. 6 times 42, I'm actually not going to do it. I'm going to just write 6 times 42 because when I divide by 7 to get x alone, I can divide 7 into 42 really easily. That's 6. And so I'm just left with 36 feet tall, which is pretty darn cool. That's all for now.